metals reacting with oxygen. Color of the flame, you need to memorize by heart. Sodium, intense yellow. Magnesium, bright white. Product form, okay, which is your sodium oxide and magnesium oxide, both are white. Okay, so they are reacting with oxygen to form your oxide, which is an ionic compound, because the bonding between metals and non-metals are ionic compound. Okay, so here, okay, look, start to recognize the trend, and when we try to understand the trend, it is easier for you to remember. Okay, so for period 3, group 1 and group 17 elements, okay, we need you to start to recognize trends, and then from there, understand and be able to regurgitate out. The same for chlorine. Okay, you can read yourself. I'm not going to go through. Okay. Now, today we'll start off with discussing the variation in oxidation number for the period 3 oxides and chlorides on page 13. Just by looking at this table, okay, you can see that the chlorides form, okay, for period 3 elements and the oxide form, all of them actually have positive oxidation number. Then you need to start to recall atomic structure. Why is it that they have positive oxidation number? Okay, when I look at chlorine and oxygen, these two are actually more electronegative. Okay, so in our syllabus, okay, generally you need to know that for fluorine, your oxygen, your nitrogen, and also your chlorine, they are the 4 electronegative atoms that you need to know. Okay, so when all of my period 3 elements are bonded with them, they will have a positive oxidation number. Okay, so here, that is the first point that we want to talk about, because O and Cl are more electronegative, so that is why you will have a positive number. Okay, then the maximum oxidation number across period 3 actually increases from +1 in sodium chloride to actually for your sulfur, okay, it can be a +6. So how do we determine the maximum oxidation number? Okay, I want to refer you, okay, you should have a point that shows the electronic configuration, or specifically the SPDF notation of sulfur and phosphorus. If I represent, okay, for sulfur at the ground state, what do I mean by ground state? It is of the lowest energy level. The electronic configuration that it will have is 1s2, 2s2, 2p6, 3s2, 3px2, 3py1, 3pz1. There are no electrons occupying the 3d orbitals. What happens is that the 3d orbitals that is present in the sulfur is actually what we call empty and energetically accessible. Because of this, the electrons occupying the 3s and 3p orbital is able to be excited and move on to the 3d orbital. So if you see the one s represented with an asterisk, this will mean that sulfur is in what we call the excited state. It has a higher energy level. Over here, with this asterisk, it shows that the sulfur is of a higher energy level. Okay, what happens is that the electrons occupying the 3s orbital has gained enough energy and then moved to the higher energy 3d orbital. So you can see that now I have 3s1, 3px1, 3py1, 3pz1. Okay, then one electron occupying the 3d orbital and another electron occupying another 3d orbital. If I go and count the number of electrons, there are a total of 6. So sulfur, the maximum oxidation number that it can form is a +6. Okay, give you around 1 minute to digest this. So in terms of the trend, I don't think it's hard to recognize that for sodium in group 1, okay, it will have a maximum oxidation number of +1. Magnesium in group 2 has a maximum oxidation number of +2. Aluminium +3. Silicon group 14. Okay, so the highest oxidation number is a +4. Okay, but here I need you to start to be able to see that if I compare phosphorus, okay, you can see that it has +5 and it can also has +3 oxidation number. The reason is what we have explained. It is the same. Okay, for phosphorus, because of the presence of the empty energetically accessible 3d orbitals, so the electrons in the 3s and 3p orbital can gain enough energy to be promoted, okay, to the higher energy 3d orbital. Because of this, so that is why your sulfur and your phosphorus will have what we call variable oxidation number. To put it in layman term, it has more than one oxidation number. So here, you need to know that for phosphorus, for sulfur, okay, it has more than one oxidation number. Is that clear? Okay? Okay, so after talking about this, okay, let's just look at the next part. Okay, we want to talk about the structure and bonding of chlorides, period 3 chlorides, and their reaction with water. Now, if you look at the periodic table, across the period, what happens is that across the period for your periodic table, okay, you will see that the elements changes from metallic to non-metallic nature. Okay, metallic meaning to say sodium, magnesium, aluminium. Okay, silicon being a metalloid, phosphorus and sulfur are non-metals. What happens is that, okay, when they form a bonding between, okay, the period 3 elements with chlorine to form your chloride, okay, I need to first compare the electronegativity. Meaning to say, okay, taking sodium for example. Okay, sodium, okay, and then it forms a bond, okay, with your chlorine. Okay, I know that across the period, first thing, I recognize that the electronegativity increases across the period. When electronegativity increases across the period, okay, for elements, if I compare between sodium as compared to difference in electronegativity between sodium and chlorine, as compared to if I compare between aluminium or rather phosphorus with chlorine, you can see that the difference in electronegativity decreases across the period. Can see? So that is why, okay, because of this, it will affect the type of bonding that the compound can have. For sodium and chlorine, because the difference in electronegativity is large, so the type of bonding that I have is ionic. This is what you learn in O level, am I right? Okay, metal, non-metal will form ionic bonding. Then, okay, if I compare between phosphorus and chlorine, the difference in the electronegativity between phosphorus and chlorine decreases. Now there is a smaller difference in electronegativity between phosphorus and chlorine. The type of bonding will actually become covalent. Okay, so here I need you to understand that when we say that, oh, a specific type of bonding is ionic and covalent. Okay, so now, okay, that is what we learn in O level. Okay, when we come to A level, okay, ionic is one end of the spectrum, covalent is the other end of the spectrum. So usually the type of bonding lies in between your covalent and ionic bonding. Okay, so over here, recognize that how is it affected is by the difference in electronegativity between the two elements that are being bonded together. Can get? So the bottom line is if you have a large difference in electronegativity, the type of bonding that is predominant will actually be ionic. If you have a very small difference in electronegativity between the two elements, the predominant type of bonding will be covalent. Can? So how does the type of bonding affect, okay, how the chlorides react with water? That's what we're going to look at. Okay, generally, across the period, when you try to react the chlorides with the water, it will form a solution that becoming increasingly acidic. I repeat again, generally, when you react your period 3 chlorides with water across the period, okay, the solution becomes increasingly acidic. Why? Okay. Okay, before I start, okay, you can see that all the equations that are highlighted in red, you need to know them by heart. You need to be able to write them out, okay, during exam. Okay, commonly tested, so you need to be able to write them out. Okay, so I'll go through them first. Okay, then we try to understand what is happening, and it makes life easier for you to remember. First thing, okay, we say that when I react my sodium chloride in water, it dissolves in water, it undergoes a process of what we call hydration. It's a big sounding word. If I put it in layman term, hydration simply means that the water molecule surrounds your ions. I repeat again, hydration, if I put in layman term, it simply means your water molecule surround your ions, forming what we call an ion dipole interaction. If I show you the diagram, it simply looks like that. Okay, for example, if I have a magnesium ion, this magnesium ion will be surrounded by 6 water molecules. Okay, it will form an interaction between the positively charged magnesium cation and the partial negative charge on the oxygen of the water molecule. This is what I call a hydration. Okay. So recognize that hydration is simply your water molecules surrounding your ions. Okay, so sodium chloride undergoes hydration to form a neutral solution. Okay, it will form Na plus and Cl minus. So the solution is actually at pH is equal to 7. Okay, so here, right, one easy way to remember is that you know table salt. Table salt that you eat at home. I mean, you don't eat the salt, but you use it for cooking. You dissolve the salt in water. Okay, the pH of the solution needs to be 7, neutral. It doesn't make sense that you add the salt inside, then the soup that you cook becomes either alkaline, which is soapy, or no acidic. Do you understand? So this is one way to remember that for sodium chloride, it will form a solution of pH 7. Can? Okay, so here, what happens is that sodium chloride solid dissolve in aqueous solution to form sodium ions and your chloride ions. State symbols, you need to know. Okay, so take note of the state symbols as well. Solid, okay, becomes aqueous ions in aqueous solution. Can follow so far? Yes? Okay, never mind. Now, next part, okay, I look at magnesium chloride. Magnesium chloride, okay, same thing as sodium chloride, it will undergo what we call hydration. So the Mg2 plus, the magnesium ions, will actually be surrounded by your water molecule. And then we call this a hydrated ion. Okay? Makes sense, right? Hydration, hydrated ions. So what happens is that, I think some of you may be wondering, oh, Mg2 plus AQ, is it the same as if I write it as MgH2O62 plus? They are the same, but the reason why we want you to write 6 water molecules surrounding your magnesium ion is because of the next step of what is going to happen, of what we call a hydrolysis. Your Mg2 plus ion, okay, will actually, the hydrated ions will actually react with water molecule, okay, to form an acidic solution. Okay, so hydrolysis is your hydrated ions reacting with water molecule. Hydration is your water molecules surrounding your ions. Take note of the difference between these two. Okay, so before I go to the explanation here, I just want you to look at this diagram. So what happens first is that when I try to dissolve your magnesium chloride in aqueous solution, the Mg2 plus will first undergo hydration. The Mg2 plus will be surrounded by 6 water molecules. Okay, it will be surrounded by 6 water molecules. And then after that, what is going to happen is going to react with the water molecule to undergo what we call hydrolysis. Why does hydrolysis take place? First, you look at Mg2 plus. It has a charge of +2. Okay, then it is a relatively small cation. Hence, we say that this Mg2 plus is what we call having a moderately high charge density. because of this high charge density, it forms the ion dipole interaction with the water molecule. Okay, so what happens is that it will actually polarize the OH bond in the water molecule. What do we mean by polarize? To put it simply, it will weaken the OH bond that is present in the water molecule. When this OH bond is weakened, eventually the OH bond will break. The hydrogen with the partial positive charge will leave as a H+. And based on what we learned in acid and bases, okay, when you donate a H+ away, okay, it is able to form your acidic solution. Okay, I give you 1 minute to digest this first, okay, before I continue. Okay, so very quickly, okay, running through again, what happens is that the compound will undergo hydration, okay, followed by very slight hydrolysis. Take note of the word slight hydrolysis. Why slight hydrolysis is because the Mg2+ has a moderately high charge density, okay, because it has a higher charge density as compared to your sodium ions. So that is why you see that for sodium chloride, it does not undergo hydrolysis, but for your Mg2+, is able to undergo hydrolysis. If I want to represent, okay, this by equation, what happens is that your Mg2+, solid state, dissolve in water to form MgH2O6 2+. Take note of how I represent. Here I'm representing 6 water molecules surrounding your magnesium ion. Why I need to show this? Okay, this is effectively the same as saying that it is an Mg2+ in aqueous solution. But I want to show the 6 water molecule is because what happens is that one of the water molecule, the OH bond, will actually be polarized and weakened. It will lose, okay, it will donate a proton to the water that is present. So this is like a acid-base reaction. Then it will form your MgH2O5 OH. Take note that over here, it becomes a plus. From a 2+ become a plus because I know that OH is a minus. Right? So that is why there's a decrease in the overall charge. Then, okay, the product form is that it's going to form a H3O+. With the presence of H3O+, the solution becomes acidic. So take note that for the pH of the solution, okay, when you dissolve magnesium chloride, the pH is going to be 6.5. Ken? Okay. Moving on, okay, when I look at aluminum chloride, okay, take note that, okay, the steps are very similar. First, your aluminum chloride will undergo hydration. When it undergoes hydration, you can see that your AlCl3 in solid state, okay, will be surrounded by 6 water molecule again, okay, to form your AlH2O6 3+. Okay, then when this is formed, okay, then I need to start to recognize that, oh, Al3+, plus 3 charge. Okay, it will have a small size, high charge density, high polarizing power. With the high polarizing power, what happens is that the same thing happens. The OH bond in the water molecule is going to be polarized. When it is polarized, the OH bond present in the water molecule is going to be weakened and the OH bond will break. The H with the partial positive charge will leave as a H+ ion. Okay, meaning to say that it will actually make the solution acidic. Okay, and then what happens is the same. Okay, you can see that the equation is almost the same. Just take note that for the product that is formed, there is a decrease in the charge from +3 to 2+. Over here, recognize that the pH of the solution is not 6.5. It is actually lower or more acidic. why is it that the solution when you dissolve aluminum chloride as compared to magnesium chloride, aluminum chloride is more acidic? Why? Okay, look at the Al3+. Al3+ actually have a higher charge density as compared to Mg2+. So that is why it is able to undergo further hydrolysis. Okay, whereas for Mg2+, okay, with your water molecule, it is only able to undergo slight hydrolysis. So the difference is because of the charge density of your cation. Okay, so here, few things that you need to know. Okay, you need to be able to balance out the equation with state symbols. Okay, and also be able to describe out that the first step undergoes hydration followed by hydrolysis. First is your water molecule surrounding your cation, followed by one of the OH bond in your water molecule being polarized and broken and leave as a H plus to form your H2O plus. Because of this acidic solution, pH of 2:3. The ones that I put the tick, you must be able to describe out. Okay? There's just an exception. If you are using limited water, what happens is that you will see that your AlCl3 react with your water, the limited water molecule, to form your hydroxide and also your HCl gas. Okay? Can? So here, I need you to take note of a few things. Describe out the first step to be hydration, represent it with an equation. Okay? Then the next thing that you need to know is that it will undergo hydrolysis, represent it with an equation, explain why is it that it's able to undergo hydrolysis, able to state the pH of the solution to be 2:3. Is that clear? Okay? So the ownership is really on all of you, to make sure that you understand and able to recognize the trend. So over here, I'm comparing between sodium chloride, magnesium chloride, and also your aluminum chloride. So overall, you can see that sodium chloride undergo hydration, magnesium chloride moderately charged density undergo hydration followed by slight hydrolysis. Aluminum chloride, same thing, undergo hydration followed by your hydrolysis. Okay? Now, let me just show you a quick video of what is happening if you react water with aluminum chloride. Okay, so this is aluminum chloride solid. Okay, this is if you are using limited water. Can you see that once you add limited water inside, what happens? What is this white color fumes? This is actually your white fumes of HCl. Okay, if I refer you back to what we learned, can you see that if I add droplets of water, I'm using limited water, it will undergo hydrolysis and produce white fumes of HCl. So the white fumes that you see over here is actually your HCl. Okay, so just take note of this. Okay, so if you are feeling sleepy, you can just go and wash your face or whatever. Okay, I think some of you are nodding off. Okay, the next one is your silicon chloride. Silicon chloride, what happens is that if you have if you have chlorides that has a simple molecular structure, it will just undergo hydrolysis. So the compound will undergo hydrolysis. Hydrolysis simply means that it will react with water. Okay, when it reacts with water, it actually forms your silicon dioxide and also your HCl gas. Okay, so this white fumes of HCl, then because of white fumes of HCl, some of it will be able to dissolve in your aqueous solution. So that is why the pH of the solution is 1:2, very acidic. Okay. So take note, okay, the equation you need to know, the state for silicon chloride is actually in liquid state. Then silicon dioxide is in solid state. You will form gaseous HCl. Okay, equation you need to know, pH 1:2, complete hydrolysis. 3 things, please take note. Okay, same thing, if let's say I have phosphorus, just take note that over here I'm more concerned with PCl5. Okay, PCl3 is not stated in the syllabus, but it's good for you to know what is happening, okay, in case they give you a contextual question. So PCl5, okay, I know that it is a simple molecular structure. Generally, for simple molecular structure, for your chlorides, it will actually undergo hydrolysis. You see, it is the exact same thing as your silicon chloride. Hydrolysis, okay, what happens is that it will form your phosphoric acid, H3PO4 in aqueous solution. It will also form your HCl. So that is why your solution is very acidic. Equation that I highlighted in written in red, you need to know by heart. PCl5 is in solid state. Okay, then it will form your H3PO4 in aqueous solution and HCl in gaseous state. Just take note that over here, if you are using limited amount of water, it will first form POCl3 in liquid state. Then this POCl3 will further react with your water molecule, okay, to form your H3PO4 and 3 moles of HCl. Okay, so maybe let me just show you some video again. Okay, silicon tetrachloride. You can see that it is in liquid state, your silicon tetrachloride. Okay, so what happens is that, okay, there's water inside. Okay, once, okay, you can see that it forms actually if you put a blue litmus paper, it will turn red, okay, because of the presence of the HCl gas that is being produced. Okay, so similarly, if you have a this is not inside your lecture notes, but I just want to show you for your disulfur chloride. So once you add it in, you can see that you actually form HCl. Okay, so generally, okay, the general trend that you see is that, okay, simple molecular structure, generally it will actually produce when it reacts with water. The process is called hydrolysis. It will produce HCl. So one of your product will be HCl in gaseous state. Okay, so please remember that. Okay, now, okay, just a quick exercise for all of you. Okay, you can draw it inside your lecture notes. Okay, if I want you to sketch a graph to show the pH of the chlorides of elements from sodium to phosphorus, and also try to explain with the aid of balance equation, describe an account for the pH value of aqueous chlorides. Can you try to do that now? Okay, so okay, this exercise is just a quick summary for yourself. Okay, so if I do the quick sketch, okay, you can see that for your sodium chloride dissolved in aqueous solution, it undergoes hydration, okay, to form a neutral solution. That's why I tell you the starting point that you need to understand is that for salt solution, which is your sodium chloride dissolved in aqueous solution, pH is neutral at 7. Okay, so that is the first thing that I'll remember. Then I know that across the period, okay, the chlorides when dissolved in aqueous solution, it becomes more acidic, means that the pH will decrease. So magnesium chloride undergoes hydration followed by slight hydrolysis, so that is why the pH is 6.5. Aluminum chloride undergo hydrolysis as well, pH is 2 to 3. Then you can see that for silicon chloride and phosphorus pentachloride, it will actually dissolve. Okay, it will undergo hydrolysis to form a pH of 1 to 2. Okay, so here this is the general trend. If let's say I ask you, the pH of your period 3 chlorides dissolved in aqueous solution are all less than or equal to 7. Is it true? Duh, right? Because it's all less than 7, right? So yes, it is true. Okay, so you need to be able to explain, okay, in particular, why is it that for aluminum chloride, it has a pH of 2 to 3. Okay, so first thing, you need to be able to describe out in words. Are you all able to see at the back? Can see? Never mind, let me just increase the size. Now, first thing, okay, I need to say that it undergoes hydration. I'm showing you, if let's say I'm marking for this question, how will I mark? First, I'll look for hydration. Did you mention this keyword hydration in your answer? Then, next, I'll look out for the equation to represent the hydration of AlCl3. Okay? In this equation, you need to make sure that you include the state symbol, solid aluminum chloride. Okay? It will form the aqueous ions. Al, okay, 3 plus being surrounded by 6 water molecule. Okay, so this is the first point I'll check. Second, after it forms your hydrated ion, this hydrated ion with 6 water molecules surrounding your aluminum cation will undergo further hydrolysis. I will check for this word, whether you mention the word hydrolysis. Then I check your equation. How do I check? The common mistake definitely some of you will make is that from Al3 plus, it will become 2 plus in your product. Because I know that once one of the H plus is donated away as a proton, what is left behind is the OH minus. So the overall charge will decrease from plus 3 to plus 2. Okay, so this will actually form the second mark. Okay, is that I check the equation, whether all the state symbols are included. Okay, I check the charge, whether there's a decrease in the charge. Okay, represented by a reversible arrow. Okay, then the last point is for me to explain why is it that it is able to undergo hydrolysis. Al3 plus have what we call the high charge density. Okay, is able to polarize water molecule, resulting in the breakage of the OH bond. So that is why it forms your H2O plus. Because it forms the H2O plus, so that is why I can conclude that the pH is 2 to 3. So these 3 points must be included in your answer. Okay, tested before, so please make sure that you know how to explain. Okay, I'm giving you some time to write it down. Okay, it's because I want you to practice writing the equation. Okay, go back. Okay, during your free time, you have nothing to do. Okay, just look through this set of notes and then write out the equations. Okay, for your period 3 chlorides when you dissolve it in water. Okay, now moving on. Okay, the next part, okay, after I talk about the chlorides, now I'll talk about my period 3 element, okay, the oxides of my period 3 elements, okay, and what are their reactions with water. Firstly, the same thing again, I try to look at the bonding and correlate it to the type of reaction with the water. So first thing is that metallic to non-metallic, okay, there's a difference in electronegativity between the oxides will decrease. So it changes from ionic, which is your sodium oxide, magnesium oxide, and your aluminum oxide, okay, to a giant covalent, which is your silicon dioxide, and then to simple covalent, okay, like your P4O10 or your SO2, SO3, okay. So here, let's just look at sodium oxide first. Now, sodium oxide has a giant ionic structure. Okay, it is very soluble in water. Okay, why is it very soluble in water? Try to recall what you learned in chemical bonding. Okay, because the aqueous ion, okay, once you dissolve in water, the aqueous ions will actually form extensive ion-dipole interaction with water molecules. Once you form an interaction, it will release energy. The energy is enough to be taken in to overcome the ionic bonds, okay, the electrostatic attraction between your oppositely charged ion. Okay, so that is why, okay, you can see that your sodium oxide can dissolve in water. Okay, because it dissolves in water to form sodium hydroxide. Sodium hydroxide is strong alkaline, so that is why the pH of the solution is 13. When you dissolve your sodium oxide in aqueous solution, you will get a pH of 13 for that solution. Okay? Now, some of you may be confused about the solubility, so let's just revisit the concept of solubility of ionic compounds again. Can you look at page 18? Okay, I'm going through this as a quick recap for all of you. Okay, solubility of ionic compounds. First thing, if I have an ionic compound, for example, a sodium chloride, okay, a sodium chloride salt, when I try to dissolve this sodium chloride salt, first thing is that when I dissolve it in, okay, the sodium ions, the chloride ions, will be able to form what I call an ion-dipole interaction with water molecule. When you are trying to form interaction, when you break interaction, you take in energy. When you form interaction, you give out energy. So, okay, when they form the ion-dipole interaction highlighted in yellow with water molecule, okay, it will actually give out energy. And the energy given out, okay, is actually enough, okay, to break the strong ionic bonds between the electrostatic attraction, for the strong electrostatic attraction between the sodium ions and the chloride ions. When the energy is sufficient, okay, your sodium chloride is what we call soluble in water. Do you understand? So there are two parts to it. The first, I look at the interaction between what I call the solvent, which is the water, and the solute, which is your sodium chloride. When the interaction releases enough energy to be taken in, okay, the interaction, to overcome the interaction between the solute, then we can say that the solute is soluble in the solvent. Do you understand? I'm not trying to rap. It's what you have learned before. Okay, so take note. Can? Okay, so that is the concept that we're trying to apply here. Okay, So now I bring you back to magnesium oxide and aluminum oxide. We know that sodium oxide, which is has a giant ionic structure, can dissolve in water. But my ionic compound magnesium oxide and my aluminum oxide, okay, you can see that the solubility in water decreases. Okay, because they decreases, you can see that magnesium oxide is slightly soluble in water. Okay, because it's slightly soluble in water, your magnesium oxide okay, can partially dissolve in water to form your magnesium hydroxide. So the pH is still alkaline, around 9. Okay, but if I look at aluminum oxide is insoluble in water. The solid cannot dissolve in water at all, so the pH remains as 7. Why is it not able to dissolve in water? Because the energy released from the ion dipole interaction of your Al3 plus and your O2 minus ions, okay, with water molecule, the ion dipole interaction, the energy release is not enough to overcome the strong ionic bonds in Al2O3. Okay? Here, okay, if you look at the table on page 18, you can see that I'm comparing two factors, the lattice energy and the enthalpy change of hydration. When I have Al2O3, what happens is that your Al has a charge of +3. Okay, so when the charge becomes larger, the lattice energy will be the magnitude of the lattice energy is larger, meaning to say that the ionic bonds form become stronger. So the energy that is needed to break these stronger ionic bonds is more already, right? Because it becomes stronger, I need more energy to break this ionic bond. But the energy release, okay, from the ion dipole interaction, the ion dipole interaction also depends on the charge on the cation. The charge is higher, but now, okay, because the increase is relatively smaller, so the energy release from the ion dipole interaction between Al3 plus ions and water molecule is not enough to break the stronger ionic bonds formed between your Al3 plus and O2 minus. So that is why your Al2O3 is not soluble in water. Understand? Okay. No reply. Got it? Yes. Okay. Can? So take note, okay, that if you dissolve magnesium oxide, the pH of the solution is going to be 9. If you dissolve aluminum oxide, it will still remain at 7 because nothing dissolved. The solid still remain behind. Now, moving on, okay, if you look at, go through this. If you look at page 19, okay, when I have silicon dioxide, the concept is the same. Silicon dioxide, you know that the energy, if let's say, okay, you want to dissolve it, you need to break the strong covalent bond between the silicon and oxygen atom. So the energy release, okay, when it forming weak instantaneous dipole-induced dipole interaction between your silicon dioxide molecule and water molecule is not enough to break the strong covalent bonds between silicon and oxygen atom. So silicon dioxide, the pH of the solution is also equal to 7. Okay. Now, if let's say, okay, I have my P4O10, okay, P4O10, okay, there's P4O6 and P4O10. Okay, P4O6 is not stated in your syllabus, but it's good to know. Okay, P4O10, when it reacts with water, it will form a highly acidic solution. Why will it form a highly acidic solution? Because it will form a phosphoric acid, okay, H3PO4, 4 moles of it. Okay, so take note that P4O10 in solid state can dissolve in your water to form H3PO4. This equation you need to know by heart. Okay, so I know that for P4O10, the simple molecular structure is able to dissolve in water to form a highly acidic solution. Similarly, okay, SO2 and SO3, they are also simple molecular structure. So simple molecular structure can react with water again to form a highly acidic solution, okay, of H2SO3 or H2SO4. So the pH is 1 to 2. Okay, so if let's say very quickly, okay, I want you to sketch a graph to show the pH of the oxides of elements, okay, sodium to phosphorus, okay, to show the pH of the solution. Okay, when oxides of the element from Na to P is dissolved in water. Okay, can you do a quick sketch? Sketch a graph to show the pH of the solution when oxides of elements, sodium to phosphorus, is dissolved in water. Okay. So when I look at this, right, the first thing I'll take note of is that, oh, aluminum oxide, silicon dioxide cannot dissolve in water. So most likely the pH of the solution should be 7. Okay, so here please remember that aluminum oxide, silicon dioxide cannot dissolve in water. The pH is of the solution will be 7. Sodium oxide, magnesium oxide, okay, can dissolve in your aqueous solution. Sodium oxide dissolve to form sodium hydroxide, strong alkaline, pH is very high. Magnesium oxide dissolve slightly, okay, so it will form a weakly alkaline solution of pH equal to 9. P4O10, okay, can dissolve, okay, can react with the water to form a highly acidic solution. Okay, so you should be able to get out a graph like that. Okay. So make use of these two graphs, you go and compare. If you dissolve your period 3 chlorides in water, what is the pH of the solutions as compared to if you dissolve your period 3 oxides in water, what is, okay, the resulting pH? Okay, go and compare between these two. Okay, and then go and recap on how to write out the equations. Like I told all of you, this part of the syllabus really depends on how much effort you put in. Okay, we can tell you a billion times, but if you don't want to sit down and understand what is happening and try to memorize the equations, you can do no shit. Okay, Ken? So that's all. I pass to Mr. Tan.
Okay, we'll continue with the rest of this topic when we come back from the March holidays. Okay, so term 2, week 1, we'll still continue with periodicity. So for the coming March holidays, okay, there's a March holiday assignment for you to do. It's all on organic chemistry. Why? Because after your holiday come back, you have a first test is on organic chemistry. Remember, it's term 2, week 1, Friday. Okay, it's all your topics. Test on all the organic chemistry topics. All right, understand? Another thing you can collect. So where is this March holiday assignment is available at photocopy shop. Should be able for you to collect already. The other thing you need to collect by Friday, okay, is your